In the next hour, I will take you on a fantastical journey through the vast, star-strewn sea of the cosmos. Please prepare yourself. Our exploration of the universe is about to begin. We often think of the universe as an infinitely deep and impenetrable darkness, pierced only by the occasional, lonely glimmer of starlight. However, hidden in the profound depths of space are magnificent wonders beyond the imagination of humanity on Earth. The crimson glow of nebulae, the brilliant blue light of giant stars, and the scorching ultraviolet radiation of quasars all weave together to form the breathtaking and splendid tapestry of the cosmos. Our journey begins near the Orion Nebula. We will then fly along the brilliant spiral arms of the Milky Way, traversing dazzling star clusters and mysterious dust clouds. Next, we will cross the cold vacuum to reach the majestic Andromeda Galaxy and traverse the dark abyss formed by giant cosmic voids, great rifts in space. Finally, we will gaze upon the entire universe, witnessing how the eternal laws of nature govern its chaos and disorder. Scattered throughout the Milky Way are numerous stellar nurseries. Some are relatively small, while others stretch for tens or even hundreds of light years. These immense nebulae, composed of interstellar gas and dust, are being relentlessly compressed by gravity. Against the backdrop of the cosmic abyss, most of these nebulae are nearly invisible. However, some structures can be observed from Earth with the naked eye. The Great Orion Nebula is one such example. This celestial object, located 1,344 light-years from Earth, is situated in the middle of Orion's sword, an asterism formed by 3 stars in a straight line. Due to its enormous size and relative proximity, the nebula has captivated scientists since the early days of astronomy. As a result, this massive structure has become one of the most thoroughly studied objects in the sky. In 1993, the Hubble Space Telescope first transmitted images of the Great Orion Nebula, allowing us to appreciate its rich colors. Most of the material appears in red or blue-violet hues. Spectral analysis revealed an unusual bright green light in certain edge regions, a phenomenon that long puzzled scientists because the observed radiation did not match any known chemical element. Some even proposed the existence of a hypothetical element called nebullium, speculating that this element, non-existent on Earth, was widely distributed in cosmic clouds. But as science progressed, it was discovered that this light was emitted by extremely rarefied, ionized oxygen. This discovery also solved the mystery of the strange glow of many other nebulae, including our own suns. To date, more than 3,000 stars have been discovered within the Great Orion Nebula, along with giant interstellar gas clouds and numerous protostars. All of these varied and astounding celestial bodies are concentrated within a region about 23 light-years in diameter, continuously engaging in complex and exquisite interactions. The total mass of matter gathered here is equivalent to about 10,000 solar masses. As we look closer at the Great Orion Nebula, we can identify several distinct regions. The most prominent is called the Trapezium Cluster. This open cluster, about 300,000 years old, consists of 8 main members, some of which are binary systems and others isolated stars. The brightest within the trapezium are 4 star systems marked with Latin letters, densely packed within a region about 1.5 light-years in diameter. Each has a mass between 15 and 40 times that of the Sun, indicating that these hot stars are very young. Among them, Theta superscript 1 Orionis C is a blue-white main sequence star and the heaviest and brightest star in the entire nebula. With a mass of about 40 suns and a radius 8 times that of our Sun, its surface temperature is around 45,000 Kelvin, and its luminosity is 250,000 times greater than the Sun's. The radiation from this star illuminates almost the entire nebula, yet there is hardly any interstellar gas near it. This is because the intense stellar winds typical of such objects blow the tenuous material far away. A few light-years from the Trapezium Cluster, we encounter another famous multiple star system, Orionis C2. It is composed of 3 stars bound together by gravity, located near the glowing region of hot gas known as the Orion Bar. Long obscured by dust clouds, clear images of this region were only transmitted after the launch of the James Webb Space Telescope. The largest star in Orionis Z2 is slightly less massive than the largest in the trapezium, with a surface temperature of about 35,000 Kelvin. The second star has a mass about 15 times that of the Sun and is 120,000 times as luminous, while the third has 5 times the Sun's mass and a temperature near 14,000 Kelvin. But it's not just bright stars that attract astronomers. The Webb telescope's infrared cameras have also discovered unprecedented objects deep within the gas and dust clouds, about 180 so-called protoplanetary disks. These are rotating disk-like structures of gas and dust that surround newly born young stars. One of them, named Orion 294-606, has a diameter of 913 astronomical units and is uniquely angled toward Earth, allowing us to clearly observe its structure and size. In a few million years, it is expected to enter the main sequence stage and may form a system with multiple exoplanets. The night sky on these future worlds will surely be fantastically beautiful, with the light of densely packed stars shining through colorful, glowing nebular curtains, and giant vortices of luminous gas occasionally covering half the sky, turning night into a translucent twilight. If we pull our view back to observe a wider area, we see that the main body of the nebula is filled with tenuous gas. The central part is filled with highly ionized hydrogen, which constantly absorbs high-energy stellar radiation, heating the gas to 10,000 Kelvin. At the edges, however, the temperature drops sharply. The pressure difference and the collision of stellar winds cause the material in the nebula to move at high speeds through space, forming giant vortices larger than our solar system with speeds up to 50 kilometers per second. In some areas, thin, filamentary structures stretching for several light years have been detected, composed of relatively cool molecular hydrogen mixed with methane, ethane, and water. Further out, the central region of the nebula is enveloped by a vast, colder, and denser gas cloud. Here, the glow of bright stars and ionized hydrogen intertwine to form a splendid, multicolored curtain of light. Although hundreds of objects are hidden behind it in the visible light spectrum, the infrared lenses of modern telescopes can penetrate this interstellar veil. By combining observational data from multiple sources, astronomers have discovered about 700 protostars in this region at various stages of evolution. The birth of new stars typically originates from the gravitational collapse of interstellar gas clouds. In this process, a giant molecular cloud fragments into multiple dense gravitational centers, which then further evolve into protostars. Such clusters are vividly described by scientists as stellar cradles. At a certain point, when the internal pressure of the compressed gas counteracts gravity, the protostar enters a temporary state of equilibrium. The remaining material forms a huge swirling disk that is gradually absorbed by the future star, while the rest is ejected far beyond the boundaries of the protostellar system. The strengthening magnetic field of a young star also forces ionized particles to accelerate and escape along magnetic field lines. The speed of this gas flow can reach hundreds of kilometers per second. When these high-speed particle streams collide with surrounding gas clouds, they form large vortices and hemispherical structures known as Herbig-Haro objects. During this process, some kinetic energy is converted into light and heat, giving these bizarre structures their different colors. Furthermore, the ultra-fast motion creates shockwaves that can be captured by telescopes. Because a stellar cradle contains many protostars in close proximity, each producing multiple gas ejections, Herbig-Haro objects display a rich variety of shapes and colors. These shapes are unstable and transient, typically dissipating completely within tens of thousands of years, during which they can travel a distance of 1 to 3 light years. A special variant of this stunning natural phenomenon takes the shape of a fired bullet. These bullets, with diameters of hundreds of astronomical units, have also been found in the Great Orion Nebula. They move at incredible speeds, easily piercing through the thin hydrogen clouds and creating shockwaves that travel great distances. Spectral analysis shows that the tips of these bullets contain iron atoms that glow in the infrared spectrum. These bullets are about 1,000 years old, and their origin remains an unsolved mystery, though scientists speculate they may have resulted from some catastrophic event. Continuing our exploration, we discover that the Great Orion Nebula is actually part of a much larger cosmic structure, the Orion Molecular Cloud Complex. This structure, stretching for hundreds of light years, covers almost the entire constellation of Orion in Earth's night sky. Here lies the famous Horsehead Nebula, named for its shape resembling a horse's head. It is a dense dust cloud 3.5 light-years in diameter, its silhouette sharply defined against a background of star-red light. Near the Great Orion Nebula is another impressive structure known as Barnard's Loop, an emission nebula about 300 light-years across that formed 3 million years ago when several nearby supernovae exploded in succession. The converging shockwaves of compressed gas jets formed this massive arc-shaped nebula. Despite its ethereal beauty, the Great Orion Nebula is a fragile and unstable object on a cosmic scale. Stellar winds, the light pressure from many young stars, and gas ejections are constantly dispersing its material into the surrounding space. The nebula has already lost about 60% of its original mass. In about 100,000 years, its remnants will be completely scattered. This shining, colorful cloud will gradually disappear, replaced by an open cluster similar to the Pleiades. The remaining young stars will travel together for a time, but they will eventually go their separate ways, finding their own places in the vast expanse of the Milky Way. Before the invention of the telescope, people could observe a band of light stretching across the sky. This captivating and mysterious phenomenon gave rise to countless legends. But it took thousands of years of scientific progress to finally unveil its true nature. The Milky Way is not a path of the gods, but the diffuse glow of hundreds of billions of stars, too distant to be resolved individually. The idea that these stars might be part of a single, giant structure was first proposed by Immanuel Kant in 1755. He also hypothesized that some of the nebulae discovered by scientists might actually be distant star groups, other galaxies. This brilliant conjecture was far ahead of its time, and his contemporaries initially refuted it. It wasn't until the early 20th century that advances in observational equipment allowed scientists to confirm the existence of other galaxies. And in 1936, Edwin Hubble designed a classification system, many principles of which are still used by scientists today. According to this system, the Milky Way is a barred spiral galaxy. Our galaxy can be considered a long-lived star, as the stars in its central globular clusters were born about 13 billion years ago. Meanwhile, star formation is still actively occurring in some regions of the Milky Way, meaning new, young stars are always being added. Data indicates the Milky Way is a relatively large galaxy on an astronomical scale. Its disk has a diameter of 200,000 light-years, with its halo extending even further into space. Our galaxy contains at least 200 billion stars of various types, 250 to 1,000 billion brown dwarfs, and over 1 trillion planets, along with countless small bodies and vast clouds of cosmic dust and interstellar gas. At the same time, conventional matter accounts for only a small fraction of the galaxy's mass. About 90% of the Milky Way's total mass is so-called dark matter. This mysterious and pervasive substance emits almost no visible light. However, dark matter plays an active role in gravitational interactions. Although most of the galaxy's mass is invisible, we can still calculate it by observing the orbits of stars around the galactic center. According to estimates, the total mass of our galaxy is between 0.8 and 1.5 trillion solar masses. The structure of the Milky Way is quite complex. Today, we will begin our journey from its center. Although this region is obscured by vast clouds of gas and dust, we can observe it through a radio window, a region of space with less dust. Like most spiral galaxies, the Milky Way has a supermassive black hole at its center. It is surrounded by an accretion disk with a radius of about 3 light-years. This black hole, known as Sagittarius A*, is the closest of its kind to us. It has a mass of 4.3 million solar masses and a radius of no more than 16 million kilometers, 3 times smaller than Mercury's orbital radius. The first images of the galactic center's black hole, obtained on May 12, 2022, with the Event Horizon Telescope, confirmed earlier hypotheses. The density of stars in the central region of the Milky Way is extremely high. More than 6,000 stars have been detected within 3 light-years of the black hole, and the orbits of some have been determined with considerable precision. For example, a blue-white star designated S2 comes within just 17.8 astronomical units of the black hole at its closest approach, moving at a speed of 6.7% the speed of light. Classical mechanics is insufficient to describe the trajectory of such a high-speed star due to significant relativistic effects. For instance, the star's orbital axis shifts by 75 arc-minutes with each complete revolution. As we traverse this region of space, we can also see several large star clusters with a total mass of about 1 million solar masses. Slightly further out, about 200 light-years away, another massive black hole with a mass of about 100,000 times that of the Sun may be lurking. Continuing onward, we will reach the central molecular zone, a regularly shaped region spanning 1,600 to 1,900 light-years with a mass exceeding 60 million solar masses. This area is home to numerous stellar nurseries, gas nebulae, protostars, and supernova remnants. The material in these clouds is primarily dense, light molecules, with temperatures fluctuating between 50 and 600 Kelvin, -223 to 327 degrees Celsius. Spectral analysis shows that in addition to hydrogen, this giant nebula contains carbon monoxide, methanol, and hydrogen cyanide. If we move away from the galactic center, we see it is surrounded by a bright, huge elliptical structure. This structure is 10,000 light-years long and about 7,000 light-years in diameter, with a total mass of up to 10 billion solar masses. This elongated oval structure forms a bar that extends for about 13,000 light-years and serves as the foundation for the galaxy's spiral arms. At one end of it, we can see the Stephenson 2 cluster, which contains the largest known star, Stephenson 2-18, with a radius 2,150 times that of the Sun. Unfortunately, the chances of finding exoplanets around this extraordinary star are minimal. Even if planets once existed, this hypergiant would have long since swallowed them during its expansion. The center of the Milky Way, with its billions of stars, undoubtedly has a large number of exoplanets. However, the probability of finding a potentially habitable planet here is much lower than in less crowded regions of the galaxy. This is because the dense distribution of numerous stars would destabilize exoplanet orbits, and their powerful radiation is lethal to all life. For this reason, a galactic habitable zone has been defined for the galaxy. It takes the form of a giant ring with a radius of 22,000 to 29,000 light-years, containing the stellar systems most favorable for the emergence of life. Inside the ring, high levels of radiation make life unsuitable, while outside the ring, a lack of heavy elements is also inhospitable. Continuing our journey away from the galactic center, we will explore its most spectacular part, the galactic disk. It is composed of 2 parts with different properties. The first is the thin disk, with a thickness of 1,000 to 1,300 light-years and a visible radius of up to 50,000 light-years, its edges gradually fading out, with the outermost stars reaching 100,000 light-years from the galactic center. About 80% of the Milky Way's visible mass is concentrated here. The thick disk has a diameter comparable to the thin disk but is 4 times thicker and much more sparse, composed of very old stars and containing almost no interstellar gas. Observations and models show that between 8 and 11 billion years ago, our galaxy devoured another galaxy, a hypothetical structure named Gaia Enceladus. It contributed billions of stars, a large amount of interstellar gas, and dark matter to the Milky Way, an event that spurred the formation of most of the thick disk and triggered a wave of star birth. Undoubtedly, the spiral arms are the most prominent features of our galaxy's disk. There are generally considered to be 2 main arms, the Scutum Centaurus arm and the Perseus arm, and 2 minor arms, the Norma arm and the Sagittarius arm. The spiral arms are regions of particularly high star density, where most of the interstellar gas is concentrated. Consequently, the star formation rate here is 3 to 5 times the galactic average. After their birth, stars exist in open clusters for the first few million years, but gravity is too weak to hold them together for long, and they eventually drift apart. Following the Sagittarius arm, we reach a fork that connects to the Perseus arm. This stellar structure, 11,000 light-years long and about 3,500 light-years wide, is known as the Orion Arm. It is here, 27,000 light-years from the galactic center, that our solar system is located. As we move beyond the galactic disk, we find the most extensive and tenuous part of the galaxy, the halo. Its visible part is spherical, extending 260,000 light-years from the galactic center but containing only a few percent of the total mass. The halo contains a large number of globular clusters composed of exceptionally old stars and several giant stellar streams. For example, the Sagittarius stream is composed of thousands of stars orbiting our galaxy in a thin, elongated ellipse, almost perpendicular to the main disk. Models show that these stars were likely captured by the Milky Way's gravity from a dwarf satellite galaxy, which will be completely consumed by the Milky Way in a few billion years. The halo is also thought to contain a large amount of dark matter, forming a dark halo that extends up to 2 million light-years and greatly contributes to our galaxy's overall stability. 2.5 million years ago, a giant star in the Andromeda Galaxy, near its core, reached the end of its life. Its final moments culminated in a cataclysmic explosion, erupting with trillions of tons of blazing plasma that formed a giant cloud, turning nearby planets and moons to dust. In 1885, a stunning astronomical event captured the attention of astronomers worldwide. An unusually bright flash appeared in the region of the Andromeda Galaxy, its light briefly outshining all other nearby stars. This amazing supernova was named S Andromedae. Its unusual parameters puzzled astronomers for a long time, but just 6 months later, the star began to dim rapidly and soon vanished from the sky forever. At that time, astronomers couldn't measure the distances to celestial objects, so this bright spot in Andromeda, also known as M31, was thought to be an ordinary reflection nebula on the outskirts of the Milky Way. This changed in the 1920s when observations by Edwin Hubble and others proved that the Andromeda Nebula was an independent galaxy similar to our own. Today, we know that the Andromeda Galaxy has a spiral structure, contains about 1 trillion stars, and has a diameter of over 150,000 light-years. A close look at Andromeda's central region reveals a unique feature that distinguishes it from other spiral galaxies, an unusual double nucleus, whose origin is not fully understood. The brighter part is a massive supercluster of many bright stars, while the other, fainter part is believed to hide a supermassive black hole about 50 million times heavier than the Sun. One hypothesis suggests that in the distant past, Andromeda absorbed a satellite galaxy, and the bright region is the remnant of its core. Another suggests the nucleus is a single structure visually separated by an opaque dust lane. Continuing through Andromeda's central region, you can also find one of its most mysterious objects. It's a binary system where a low-mass neutron star, rotating every 3 seconds, is gradually absorbing its red giant companion. The two are so close that the neutron star is eclipsed by the other star every 4 hours, causing its brightness to drop sharply before recovering. This process will continue for tens of millions of years until the second star is torn apart by tidal forces, becoming a bright, hot, ring-shaped nebula. Like the Milky Way, Andromeda has a bar structure and 2 massive spiral arms that wrap around its center. About 56% of the galaxy's stellar mass is contained in these arms, where interstellar dust and gas are concentrated, forming many star-forming regions. Among these is the remarkable star AE Andromedae, a luminous blue variable, one of the brightest and most unstable types of stars known. Due to extreme temperatures and pressures, its outer layers are in a constant state of unstable equilibrium, with its evolution being largely chaotic and unpredictable. Occasional collisions of hot plasma streams can produce extremely bright flares, increasing the object's luminosity by dozens or even millions of times, which could easily be mistaken for a supernova explosion. Our journey has now taken us far beyond our home, across the 2.5 million light-years of intergalactic desert that separates us from Andromeda, a distance that could fit 25 Milky Way galaxies. This is just a tiny part of the vast cosmic abyss. The Milky Way, Andromeda, and the Triangulum Galaxy, along with their more than 100 satellite galaxies, are bound together by gravity to form the local group, which is about 10 million light-years in diameter. The local group, in turn, is part of a larger structure called the local sheet, a flattened group of galaxies about 46 million light-years in diameter and 5 million light-years thick. The local sheet itself is part of the even larger Virgo supercluster. Shockingly, at the edge of the local sheet, normal cosmic space suddenly gives way to a giant, black abyss known as the local void. Our local sheet forms one of the walls of this void. The void's nearest edge is very close to Earth, about 3.2 million light-years away, and it occupies a large portion of our night sky. A lone dwarf spiral galaxy, NGC 6503, was discovered in the heart of this void, notable for its incredibly colorful appearance with bright red clumps of hot hydrogen and blue glowing nebulae in its spiral arms. These voids are a fundamental part of the universe's large-scale structure. They are thought to have formed from tiny density fluctuations in the very early universe, which were then amplified by gravity over billions of years, pulling matter into dense clusters and leaving vast regions increasingly empty. This process has shaped the cosmic web we see today, with the vast majority of galaxies having formed between 10 and 13 billion years ago. The Virgo supercluster, containing about 30,000 galaxies, is itself part of an even larger structure, the Laniakea supercluster. It contains over 100,000 galaxies and spans more than 500 million light-years. And yet, this colossal structure is enveloped by an even greater abyss of darkness. In 2013, astronomers discovered that our Laniakea supercluster is located in the middle of the largest supervoid known to science, the KBC void, named after its discoverers. This void is roughly spherical with a diameter that may exceed 2 billion light-years. Its discovery helped explain a long-standing paradox in cosmology concerning the expansion rate of the universe, known as the Hubble constant. The extra gravitational pull from matter outside the void slightly accelerates galaxies within it, like ours, resolving the discrepancy between local and distant measurements of cosmic expansion. Amazingly, the KBC void is so large that it contains other voids within it, such as our local void. In the southern celestial hemisphere lies another enigmatic region, the Eridanus supervoid, also known as the CMB cold spot. Estimated to be between 500 million and 1 billion light-years in diameter, it is one of the most massive elements in the universe's large-scale structure. The cosmic microwave background radiation passing through this region is about 70 microkelvins colder than the cosmic average, an anomaly far greater than any previously recorded. While gravitational effects from distant superclusters can explain some of this cooling, about 75% of the effect remains a mystery, possibly hinting at the influence of dark matter or dark energy concentrated deep within the void. A butterfly flapping its wings in Brazil can set off a hurricane in Indonesia. This is the butterfly effect, a concept from chaos theory proposed by Edward Lorenz. It means that a tiny change in initial conditions can trigger a chain reaction leading to unpredictable, major consequences. In 1961, Lorenz was trying to model atmospheric behavior with a computer. To speed up calculations, he rounded off some numbers, a seemingly insignificant change. However, the results of the continuous and staged calculations were vastly different. This led him to a stunning discovery. All possible solutions to his system were concentrated around two regular positions he called attractors, which, when plotted, formed a shape resembling butterfly wings. Any tiny change in the initial parameters could abruptly shift the final result from one wing to the other. This is deterministic chaos. The system follows strict physical laws, but they are so complex that its behavior appears unpredictable. This is different from truly random events, like the decay of a specific atomic nucleus in radioactive material. Chaos theory requires three things. The system must be nonlinear, it must be sensitive to initial conditions, the butterfly effect, and its various parts should overlap and interact as it evolves. Let's think back 13.8 billion years ago, just moments after the Big Bang. There was no matter or energy as we know it. The four fundamental interactions were united into a single, strange force, and the laws of physics were different but no less strict. Any tiny fluctuation in the nascent universe could completely alter its future. Our reality was indeed born from chaos in the scientific sense. Billions of years later, first-generation stars exploded, enriching the universe with heavy elements. New stars were born from hydrogen clouds, and surrounding cosmic dust formed protoplanetary disks, all exhibiting the familiar patterns of chaotic motion and interaction. This is how our solar system was born about 4.6 billion years ago. Our eyes can only perceive a small fraction of the universe's astonishing and colorful nature. Some of its dimensions only become apparent outside the visible light spectrum. It is only through technology that we can touch this amazing beauty. Every second, hundreds of telescopes are observing the universe, meaning that with every moment, we are taking another step toward new knowledge and discovery.